So in class so far, we've been talking about functionalization of aromatic rings, starting with a simple benzene molecule. But now we're going to start looking at substituted benzenes and what those substituents, what effects those substituents have on further functionalization. So the term we use to describe this is called directing group effects. And so directing group effects are the effects of a substituent on further functionalization. Okay, so directing groups can either be activating or deactivating, and these sort of exist on a large scale, right? From one end to the far end. On one end we have activating groups. And on the other end, we have deactivating groups. Okay? So activating groups are electron-rich groups. So some examples of that might be an OH group, an NH2 group, things that have a lone pair adjacent to the benzene ring. So we have lone pairs on oxygen, lone pairs on nitrogen. These can donate into the benzene ring and increase electron density at certain positions, right? And our scale of activating to deactivating groups, in the middle we have hydrogen, right? Where hydrogen is sort of neutral. It doesn't have a activating or a deactivating effect. It's our sort of our baseline position on this scale, right? So let's first talk about activating groups. Activating groups work because you're able to donate the electron density into the benzene ring. So if we draw out a simple aromatic compound, and we're going to use an aniline here, so an NH2 group there, what we can do is we can draw a resonance structure where we push the lone pair into the benzene ring, and we can draw the different functional groups, right? So we can take the lone pair, push it down towards the benzene ring, and we can draw a resonance structure where we put a charge on this position here. So our new resonance structure will have a positive charge on our nitrogen, and we're going to put a lone pair on this carbon, right? And that's going to have a negative charge. All right? And we can keep going, drawing resonance structures around the ring. So we can take this lone pair, push it down, and then put a lone pair on the carbon that's para to nitrogen. Right? So we're increasing electron density at these positions. So in this structure, we have increased electron density that is ortho to our nitrogen, to our aniline group. Here we have it is para, and we can keep going, where we want to localize that on this carbon here. Right? So by drawing out this resonance structure series, we can see that we put electron density at the ortho and the para positions. Right? So we're increasing electron density there. So these positions are more likely to act as nucleophiles in our electrophilic aromatic substitutions. So we say that activating groups are ortho-para directors. So activating groups, because they increase this electron density, are ortho-para directors. When we have the option to functionalize ortho or para, generally para wins out, even though there are more options to functionalize the ortho position, because we draw two resonance structures where it's possible, but it's more of a steric argument where it's a little harder for this to act as a nucleophile relative to this one. Okay? So these are the strongly activating groups. They're on one extreme of the scale, right? As we go more towards hydrogen, we have functional groups like esters here, right? So we still have a lone pair that is adjacent to the benzene ring, but now the lone pair on oxygen is in conjugation with something else. So it's decreasing its ability to donate electron density into the benzene ring. And this also applies to molecules like amides. Okay? So these are strongly activating. These are moderately activating. Something that's weakly activating would be something like an alkyl group or an alkenyl group, so a double bond. Right? So these functional groups primarily donate electron density by hyperconjugation. And we know this is a very weak effect. So generally, it's not going to be a very strong shift from our baseline of hydrogen. Right? It's just a weakly donating effect, although it is still an ortho-para director. Okay? Let's shift gears and look at the deactivating side of things now. So a deactivating functional group would be something like a nitro group, so an NO2 group. Okay? So with an NO2 group, again, we're going to draw out our resonance structure, right? We have a partial positive charge on nitrogen in one resonance structure and a partial negative formal charge on oxygen. Okay? So when we draw a resonance structure this time, we're going to be pulling electron density out of the benzene ring at certain positions. Okay? So what we can do is we can take the double bond and we're going to push it towards this oxygen. So we're going to take it, we're going to put it between nitrogen and carbon, and then take the NO double bond and localize it as a lone pair on oxygen. So this will give us another resonance structure. Where we now have an NO, or an N-carbon double bond, and two single bonds to oxygen. I'm going to draw in all our formal charges here. So we're going to have a positive on nitrogen, a negative on oxygen, and another negative on oxygen. And in our benzene ring, this position, the ortho position, is now going to be deficient electrons. So it will have a positive charge. Okay? So we can keep going. We can now take the other pi bonds in the benzene ring and push it towards that positive charge and distribute that positive charge throughout the benzene ring. So as we do that, we'll take this one and shift it up. All right, so we end up with a electron deficient carbon at the para position, and we can keep pushing the arrows around so that the other ortho position is also electron deficient. Right? So in the case of these deactivating groups, we can see that the nitro group removes electron density from the ortho and the para positions, right? Ortho positions have a positive formal charge here. Our para position has a positive formal charge. So we are decreasing the electron density at those positions, which leads to a reduction in reactivity at those positions. You can see that the two meta positions, though, right, we never put a positive charge there. right? So the meta positions are sort of unaffected, right? So we're turning down the reactivity at ortho and para positions, but meta reactivity remains the same, right? So deactivating groups tend to be meta directors. Okay, so nitro group is a classic example of this. Other examples would be things like a trihalo methyl group, so where X is a halogen atom, right? These are going to be strongly electron withdrawing, not by resonance, but instead by inductive effects, right? We also have groups like nitriles, cyano groups. They are electron withdrawing by resonance. We also have many carbonyl derivatives, right? So anytime you put a carbonyl adjacent to the benzene ring, we are going to reduce the electron density by resonance. So again, we're going to be able to draw out all these resonance structures where we have partial positive going around the benzene ring at ortho and para positions. So this applies to ketones, esters, amides, right? Anytime you have a carbonyl derivative here. Okay? So these are also meta directors. Okay? The last series of functional groups we're going to talk about are the halogens. And the halogens sort of are somewhere in between. They are going to be deactivating because of their electron withdrawing nature, because they're so electronegative. They're pulling electron density away by induction. So things like chlorine, bromine, and iodine, right? All of these pull electron density away from the benzene ring by induction. However, they all have lone pairs, right? And because they have lone pairs, we can draw resonance structures where we donate the lone pair into the benzene ring and increase electron density at these positions, right? So halogens are fairly unique, right? They are on the side of deactivating groups, but they are actually ortho-para directors. All right, so if we're going to have an equivalent scale on the top here, this is sort of where it gets cut off, where everything on this side is an ortho-para director, everything on this side is a meta director. Right? And so we can use these to sort of predict where in the molecule further functionalization will go. And when we start talking about synthesis problems, we're going to have to take into account whether or not we have an ortho or a para director and use that to guide our synthesis and decide which functional group to add to our benzene ring first.